Hi, thanks for joining me. Happy Pi Day. Well, Pi Day is actually tomorrow, or at least tomorrow from the day of upload. But today's upload day, so I thought I'd do something for Pi Day, which is tomorrow. Okay, and the reason it's tomorrow is it's on the 14th of March, because the first three digits of pi in base 10 is 3.14, so 314, and that's how you're supposed to write the date, apparently, in America. But I'm from the UK, so it probably should be 14/3. I don't know. Tomorrow's Pi Day, so I'm doing a video about pi. Anyway, in today's video, I'm going to be proving that pi is irrational, and the proof I'm going to show you is hopefully the simplest one to follow, at least the simplest proof out there at the moment about pi being irrational. Okay, it's going to be quite similar to the one, the proof I made a few videos ago in which I proved that e to the m is irrational. So yeah, it's going to have a similar flavour, so hopefully some of the steps will seem familiar. Anyway, I'm waffling now, let's get stuck into the proof. Okay, so what we want to do is prove that pi is irrational, and the way we're going to do that is by proof by contradiction. So we're going to suppose for contradiction that pi is rational, so that means we can write pi in the form a divided by b, where a and b are positive integers. So we're going to suppose for contradiction that pi equals a over b, and a and b are positive integers. Now what we're going to do is introduce a family of functions, each of them indexed by some positive integer n, and we're going to call them fn of x, and it's going to be b to the n times x to the n times pi minus x, all raised to the n, and all of that divided by n factorial. Okay, so obviously for each positive integer n, we get a new function fn of x. Okay, and I've written two claims about fn of x. Firstly, claim 1, that for x in the range 0 pi, fn of x is non-negative and is bounded from above by a times pi all raised to the n, and then that divided by n factorial. And my second claim is that the jth derivatives of fn of x evaluated at 0 and pi is always going to be an integer, and that's for j being any positive integer we like. So that just means that when we differentiate fn, j times, where j is any positive integer we want, and then plug in 0 and plug in pi, we're going to get two integers that could be the same. Doesn't really matter, but they're integers. That's the important thing. And like with my video on e to the m being irrational, I'm not going to go into these into too much detail, but hopefully we can just talk through the proofs for these. This one here, in the range 0 pi, fn of x is non-negative. Well, that's quite clear because x is non-negative and x is at most pi. So this guy here is going to be at least 0. So we've got a bunch of non-negative terms multiplied together. So that's where we get this inequality from. And to get this one here, well, clearly the n factorial is the same. So we just need to show that the numerator is at most a times pi all raised to the n. But that's kind of clear because we know that x is between 0 and pi. So this guy here is bounded above by pi to the n. So that's where we get this pi to the n from. And then this guy here, pi minus x, well, pi minus x is also bounded from above by pi because we know that x is at least 0. So pi minus x can at most be pi. So we've got b to the n times pi to the n times pi to the n. But remember, pi equals a over b. So if you multiply both sides by b, we get that a is equal to pi times b. So we have, let me just write it here, fn of x is less than or equal to b to the n times pi to the n times pi to the n. But pi to the n times b to the n is just pi b to the n, which is, oh, there's an n factorial there. This pi to the n times b to the n is just a to the n. And that's exactly what we have there. So that kind of proves our first claim. And the second claim is a bit more tedious to go into a proof for, but it's kind of clear. Let's just look at the case x equals 0. So we're plugging in x equals 0. Well, firstly, this is a polynomial of degree 2n. So if j is bigger than or equal to 2n plus 1, sorry, then the jth derivative of fn is just going to be the 0 function. So no matter what you plug in, you're going to get 0. So in particular, when you plug in 0, you're going to get 0. And of course, 0 is an integer. Cool. What about for other values of n? Well, other values of j, sorry. Well, if you plug in j being less than or equal to n, less than or equal to n minus 1, sorry, when you differentiate this guy, j times, because j is less than or equal to n minus 1, you're always going to have at least an x term out front. So when you plug in x equals 0, it's going to be 0 times something. Okay, so it's going to be 0 times something, so that's just going to vanish. And then for x being between being at least n, sorry, when you differentiate these guys, you're going to bring an n down, then an n minus 1 down, and so on. So if you're differentiating j times, you're going to have an n factorial coming down, so that's going to cancel with the bottom here, And then no matter what you plug in, when you plug in x equals 0, you're just going to get something multiplied together. And notice you're going to have a pi to the n times b to the n. But of course, pi to the n times b to the n is just a to the n, and a is an integer. So a to the n is an integer. I'm not sure if that made any sense, and that definitely wasn't rigorous. That was very hand wavy. But yeah, the jth derivatives of fn at 0 and pi are always going to be integers, but it's kind of just a bit boring to go through. So I'm going to stop waffling and move on to the next step. Okay, so now what we're going to do is introduce a new family of functions which we're going to call capital Fn of x, and they're defined as follows. It's the sum from j equals 0 to n of minus 1 to the power of j times the 2jth derivative of Fn of x. Okay, so this kind of alternating sum where we're only looking at the even derivatives of Fn of x. And now what we want to do is kind of get, not a differential equation, but write capital F in terms of its derivatives. And that's kind of why we've defined capital F to be this sum here. So what we're going to do is look at the second derivative of Fn of x. So let's just compute that. And we can kind of just do, as opposed to differentiating it once and then differentiating it twice, I'm just going to differentiate it twice straight away. So it's the sum from j equals 0 to n of the second derivative of this guy here. And the second derivative of this guy here is just Fn of 2j plus 2 of x. But of course 2j plus 2 I can just write as 2 and then j plus 1 in brackets, like so. Okay, but now remember, Fn of x is a polynomial of degree 2n. So if I differentiate it at least 2n plus 1 times, that's just going to vanish. But notice when I plug in j equals n into this summation here, I get Fn and then the 2n plus 2th derivative of Fn of x, which I've just said is going to be identically 0. So we're just adding on 0 when we add on our nth term. So we only actually need to sum to n minus 1, like so. Now what we're going to do is just do a change of sort of variables of this j. So I'm just going to say let I equal j plus 1. So this guy here is just now the sum. Now when j equals 0, I is going to equal 1, like so. And then when j equals n minus 1, I is going to equal n minus 1 plus 1, which is n. Minus 1 to the j now is just minus 1 to the I minus 1, like so. And then Fn to the 2j plus 1 derivative of Fn of x is now just the 2ith derivative of x, of Fn of x, like so. So we have the second derivative of capital F is equal to this sum here, and now this looks very similar to what we have up here, except there's a few things different. Firstly, we've got an extra minus sign here, and also our sum is going from j equals 0 here, but here we're going from 1. So what we're going to do is add on the 0th term here and then just subtract it off. But firstly, let's bring this minus sign out the front, like so. And we've just got to be a little bit careful of our minus signs here. But what we're going to do is introduce a 0 term. Let's put the minus here and then in brackets. So now we're summing from I equals 0 of this guy here, but then of course we've got to subtract off the 0th term now. What is the 0th term of here? So it's minus 1 to the 0, well that's just 1, times the 0th derivative of Fn of x, which is just Fn of x, like so. Oopsie daisy. So the second derivative of Fn of x is this guy here, or sorry, minus, and then in brackets this guy here minus Fn of x, but this guy here is precisely capital Fn of x. So this is equal to minus Fn of x minus little Fn of x, like so. So the second derivative of Fn of x is equal to this guy here, so we can just rearrange this, and it gives us that Fn double prime plus Fn is equal to little Fn, like so. Okay, so we've sort of got this, it looks a little bit like a second order differential equation, and if you think about this, we've got the second derivative of something plus that something equals something else, and if you've done any second order differential equations before, you can see that perhaps a sine x, cosine x, something like that is going to pop out of this, as we'll see in just a second. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that the second derivative of capital Fn plus Fn equals little fn, and capital Fn, just to remind you, is defined to be this guy here. Now what we're going to do is just take a little leap of faith here and differentiate a function, and we might wonder why we would differentiate this function, but once we see what it equals, things will start to fall into place. Okay, so we're going to just differentiate this function here, which is Fn prime of x sine x minus Fn of x cosine of x, like so. So we're going to differentiate this guy here just using the product rule. So this guy here, when you differentiate it, we're going to get fn double prime of x sine of x plus fn prime of x times the derivative of cosine of sine of x, which is cosine of x, like so, minus, now let's differentiate the first guy, so fn prime of x, and leave the second guy, cosine of x, and then keep this guy and then differentiate that guy. Derivative of cosine of x is minus sine of x, so the minus will cancel with that guy, so we get plus f of x sine of x, like so. But hopefully you notice these two terms here cancel quite nicely. So we're left with f double prime times sine x plus f of x sine x. But of course we can just factor out the sine x, so this is equal to sine x times fn double prime of x plus fn of x. But from what we showed before, this guy here is just little fn of x, so this is just little fn of x times sine x. Just squeeze it in there. Okay, so we've shown that the derivative of this guy here equals this guy here. And now why did I want to show this? Well, now what we can do is integrate both sides. So if we integrate this right hand side, just using the fundamental theorem of calculus, we're going to get the thing inside the brackets here. Anyway, this is all messy, and let me clear up the whiteboard and then we can continue. Okay, so we're at the final step of this proof. What I've just done is written down what we just proved and now integrated both sides between 0 and pi, and then applied the fundamental theorem of calculus, which says that if you're integrating the derivative of something, essentially the integrals and the derivatives cancel, and then you just have to plug in the top limit and the lower limit. Okay, so let's just see this look at this right hand side. For this guy here, when we plug in pi into sine of pi is 0 and sine of 0 is 0, so this thing is just going to vanish, so we just have to focus on this thing here. And now look at what capital Fn of x is. It's just the sums, and then with a plus or minus out front of this guy here, the derivatives or the even derivatives of little fn. But remember we said that at the start that the derivatives of little fn, when you plug in x equals 0 or x equals pi, you're always going to get an integer. So that means capital Fn is just going to be the sums of integers. So in particular, capital Fn will be an integer at pi and 0. So then that means that this thing here is going to be an integer at pi and also at 0. And we know cosine of pi is just minus 1 and cosine of 0 is 1. But in particular, it's an integer. So this guy is always going to be an integer. So we've got an integer times an integer, then minus an integer times an integer. In other words, just a bunch of integers, but when you look at their sums and products and whatever we're doing here, we're always going to get an integer. So this thing here is an integer. Okay, but of course this guy here equals this left-hand side. And now we can just see fn of x, remember, is non-negative in the region 0 pi, where we're integrating over. And in particular, it's not identically the 0 function, and it's a continuous function, so it's integral, or at least, sorry, fn of x times sine of x is a non-negative function in that region, because sine of x, remember, is non-negative in 0 pi. And because of continuity and the fact that it's not identically 0, this integral here is going to be positive, so strictly greater than 0. But because we know it's an integer, that means it must be a positive integer, and thus at least 1. Okay, so this thing here is positive, and then using the right hand side, which we know is an integer, combining both those things tells us that this guy equals something that is at least 1. So this is all in all, this is at least 1. But if we remember, fn of x is bounded from above by a pi to the n divided by n factorial. So in particular, sine of x in this region here is less than or equal to 1. So we know that fnx sine of x is in fact going to be less than or equal to this guy, which we know is less than or equal to this guy. So when we integrate both sides between 0 and pi, the integral from 0 to pi of fn of x sine of x dx, that's going to be less than or equal to the integral of this guy here between 0 and pi. But of course this is just a constant function. So when we evaluate that out, that's just a pi to the n divided by n factorial times pi. But now if we take the limit as n goes to infinity, you notice up until now we haven't actually cared about what n was, apart from the fact that it's just a positive integer. But now, so that means everything up until this stage applies for every positive integer n. But now what we're going to do is take the limit as n goes to infinity of both sides, and notice that this right hand side here is 0, goes to 0 as n goes to infinity, because factorials grow faster than exponents. And we know this guy here is always non-negative. And because this tends to 0, by the sandwiching theorem, this guy here will tend to 0 as n tends to infinity. But then that means that, well, that essentially contradicts this guy here, because the limit of a sequence, if a bounded sequence, must be within that bounded range. So that would imply then, if this were all true and if pi were rational, this would imply that 0 is greater than or equal to 1, because the limit goes to 0, but we've just shown that it's always at least 1. And there's no way those two things can happen. Okay, so we arrive at our contradiction. And thus, our original assumption that pi was rational must have been false. But yeah, I hope you have enjoyed this video. It's certainly probably the simplest proof I've seen of the irrationality of pi. But if you have seen a proof that is more simple, or at least another simple proof of the irrationality of pi, I'd love to see it, because those ones are a little bit more difficult to come across than the irrationality of root 2 or the irrationality of e or something like that. But anyway, thanks for watching. Hope you have a happy Pi day. I'll catch you in the next one. Have a great day.